Okay, so our final speaker for this session is Yuji Nakatsukasa, and he will talk about accuracy and stability of randomized numerical algorithms. Please, Yuji.
Thank you so much, Stefan. It really means a lot for me to be speaking here. I was a postdoc here 10 years ago, or almost 2 years, and it's fantastic to see actually most of my friends from back then. I'd like to talk about accuracy and stability of randomized numerical algorithms. Of course, this title hopefully rings a bell to most of you. And so I've been interested very much in randomized algorithms in numerical linear algebra in the past few years. And I think stability is something that many who work in the field seem to overlook. And it's something that I think is crucial for the field to keep making progress. So this book, which Sven mentioned in the morning, I agree with him. This is an absolute masterpiece. So all the important results back then are here. I think actually most of the important results today are still there. And it's just, every time I read it, I learn something new. Here's a snapshot of some of the results there that I consider important. And I think all these are actually surprising. For example, household order QR factorization is backward stable. This is amazing, especially considering Q and R, those are both wrong, but Q times R is perfect. Least squares is backward stable. These are going to be important in what follows. And none of these is trivial. I also want to mention that my first paper with Tikhonov is about stability of iterations for computing polar decomposition. It's not a famous paper, but I love the paper. I think it's a great one. So if you haven't seen it, please take a look. And so stability is very much at the heart of my research life. So once again, I'm interested in randomized linear algebra. I'm not going to be able to talk too much about it because there's so I'm trying to cover too much probably. Theo, I think, mentioned these two, so it's a great start. So classical dense algorithms are amazing for matrices of size, say 5,000. They're backward stable, incredibly reliable, impossible to break. There are iterative methods that are geared towards even larger matrices. They are great if the matrix has nice spectra or maybe well conditioned, then you can use something like LSQR. But generally, you would be needing some preconditioner to make it work. Randomized algorithms, which are the focus of this talk, are more of a recent development, which I think is very exciting. Why would you want to randomize? I would love to talk about this for 10 minutes, but I can't. So let me just say that sometimes you can get drastically improved speed. There are obvious downsides, but these days, many people are happy to say lose lack of reproducibility in exchange for improved speed. So one highlight of this talk that I wanted to emphasize is many people who work in randomized linear algebra, I think mostly come from outside the core numerical linear algebra community. And somehow that doesn't necessarily mean this, but most papers don't talk about stability, which I think is, we all agree it's important, but sometimes it's crucial. So in fact, some of algorithms that are used in randomized linear algebra are unstable. So I wanted to talk a little bit about stability in the context of randomized linear algebra. And so I'm going to talk very quickly about these 5 topics. Hopefully, you'll find at least one of them interesting, and I'll love to talk to you more about any of these over coffee or whatever. So I'll start with low rank approximation, but I guess before doing so, I want to give a high-level overview of what sketching is in randomized linear algebra. So very roughly speaking, the idea is to try and solve for a gigantic matrix. It's too big to solve a linear system or eigenvalue problem with. So we sketch, which is to say we draw a random matrix S, which is a sketch matrix, or sometimes from both sides, and try to argue that sometimes under some natural assumptions or or natural or artificial assumptions, that this matrix has enough information to solve the original problem. So massively successful stories of this idea include low rank approximation. So Hauke, Martens, and Traub, I believe most of you know, this is an amazing paper that really kind of popularized how effective randomized linear algebra can be. There's least squares. Bledin-Pick is famous. The regularized least squared, which I will talk a little bit about later. I have a paper with Joel Traub that talks about linear systems and eigenvalue problems, very much based on sketching. And I'll also talk about null space problems at the end, and many others. So I think sketching is an idea that can really sometimes change the way we think about a problem. It's not always going to work. You need to know when it's going to work. But once you're careful about how to use it, it can be very powerful. So the first example that I want to talk about is low rank approximation. So you want to approximate a gigantic matrix as a product of basically tall, skinny matrices. And this is like, at least for me, the prototypical example of how sketching can be powerful. So basically the idea is, so I call it generalized line theorem. There have been people who kind of used the expression before, and it goes back as far as 1934. Anyway, the way it works is you draw two random matrices. So sketch from the right, sketch from the left, and you kind of make ends meet by looking at this core matrix or choosing it appropriately. So surprisingly, this is a great approximation. So for the analysis, I'm going to assume x and y are Gaussian. For practical computation, it makes sense to try and take x and y to be more structured, like subsample of FFT matrix. But what one can show is it's quite remarkable. This almost lousy approximation is going to give you essentially the best low rank approximation with a slightly lower R. So this is like a rank R approximation with maybe 0.9 times R. Best low rank approximation, you're going to get the residual or the error, which is like order 1 times the best possible. So this is more or less the same type of error analysis that you can get with the Hauke, Martens, and Traub method. This is a little bit faster. Yeah. So the point that I want to highlight today is this this expression. Basically, in the literature, people have been using it without so with this pseudo inverse, which is defined through the SVD. It turns out that, at least to my mind, in order to guarantee numerical stability, you have to introduce this stabilization parameter epsilon. And not only that, it's actually even more crucial that you implement this carefully. And then this is an aspect that most papers ignore. So if you were to do pinf, you'll probably not be surprised to hear that it's going to be very unstable. Even if you do backslash in MATLAB, this is not going to be stable. So you have to be very careful in how to implement it. But if you are, then one can show it's backward stable. So it's a little bit messy, sorry. But I wanted to highlight how I prove that this algorithm, when implemented using QR, the QR factorization for solving an underdetermined linear system, is going to give you a good solution. And really, the crucial result that I use here is the backward stability of an underdetermined linear system solved using the QR factorization. So this result, I think, is actually Nick's own result with Jim demo. But so the expression is messy, but basically, we can look at this in terms of solving a series of underdetermined linear systems, and using the QR factorization, it's going to be backward stable. So we can say each row of this underdetermined linear system is solved backward stably, and you do some algebra to see that the error or the approximation error in terms of how close your computed row is to the thing that you're trying to approximate is essentially within order epsilon. So please look at my paper if you're interested. But I really wanted to highlight the crucial role that classical stability analysis plays in this analysis. So here's an experiment using a proper-ish implementation, which is really like 10 lines of MATLAB code. So generalized Lie theorem, as I call it, can be a lot faster than Helko-Martens and Trop, at the same time getting more or less the same accuracy as you increase the rank. Right, so on to topic 2. So linear systems, AX equals B. What we do here is we are going to use sketching once again for solving a linear system. And we're going to use it more precisely for the problem that arises in the context of GMRES. So I presume most of us know what GMRES is. It's already been mentioned many times today. But the idea is to try and find the best solution that minimizes the residual inside a queryable subspace. The main bottleneck is in the Arnoldi process, which orthogonalizes the new vector against all the previous vectors. And this is going to cost essentially nk squared cost after k iterations. So there's a clever way of reformulating this as an upper Hessenberg least squares problem. And this is all due to Saad and Schultz. But once again, as k, which is a number of iterations, grow, the orthogonalization cost becomes dominant and expensive. So what people usually do is they restart GMRES so that this part doesn't dominate the computation. So what we did is we wanted to think about using sketching. So the idea, once again, for tall skinny matrices, what the sketching will do is it will reduce the height of a matrix. And least squares problems is one of the first examples where sketching has been shown to be very useful. But if you think about it, once you have done Arnoldi, there's very little space for improving the speed by sketching, because it's already equivalent to an upper Hessenberg least squares problem, which is very small, k plus 1 by k. But our observation here is to note that there's no fundamental reason we had to orthonormalize the basis. So this qk spans the queryable subspace. We don't need an orthonormal basis there. We only need a basis that spans the same subspace. So these are mathematically equivalent up to numerical errors. But the point is maybe bk, a new basis which is not orthonormal, could be built in a quicker way so that we can now use sketching to good effect. So if this is quicker than that, we can now sketch and then maybe solve this. And so a classical result in randomized linear algebra is that this process is usually fine in the sense that your residual will be maybe twice as large as the optimal if you were to solve this sketched problem. Okay, so does this buy you anything? The answer is yes. So what we're going to do is we're going to build bk, which is not orthonormal. We're going to avoid the orthonormalization cost that you need in Arnoldi. And we're going to claim basically that as long as the condition number of A times bk, this matrix, is something like 10 to the 16 or smaller, it's going to be good. And this process, so solving this is good, and therefore in some sense solving that is also good. So we can really make this work. Once again, we're going to rely on a classical result in stability, which basically says that solving a least squares problem using the QR factorization is great. So the computed residual is going to be essentially the as small as you can possibly imagine. So it's as small as the best possible residual, maybe plus the error in computing actually the residual. So what it means for us is, as long as the condition number of A times bk is something like 10 to the 16 or smaller, we can actually solve this numerically, and it's going to be just as small as if you had solved the GMRES problem, which is mathematically equivalent, but we're basically saying that it's even the same numerically. Okay, so the same basically goes for the sketching step. So what it tells us, or what the benefit that we might be able to get from this, is if we're able to find a bk which is not orthonormal, but still basically numerically full rank, much quicker than using Arnoldi, then we might be able to speed up GMRES overall. what we do in our paper, this is not the final word to this topic, I hope. But what we do currently is we, instead of orthogonalizing against all the previous vectors, we orthogonalize against, say, the last 10 vectors, something like this. So as long as we don't orthogonalize against all the vectors, we can get speed up. And here's an example, or somehow the best example that we had, of where we're solving a non-symmetric linear system. We're comparing GMRES with the sketched version, and also the restarted versions. And basically, the idea is the convergence is almost exactly the same as GMRES. So we're a little bit higher because we're sketching, and that leads to like typically like 10% suboptimality. In terms of speed, we're really gaining a lot because we're sketching and we're not orthogonalizing the Kuhla basis matrix. So we're getting like a 200 x speed up here, and we're even faster than restarted GMRES. Okay, so on to the third topic, eigenvalue problems. So as I mentioned in the introduction, if the matrix size is like larger than 5,000, the amazing QR algorithm starts to grind to a halt. So what people do is they use subspace methods. So the idea is to work with a subspace. So this is a very tall, skinny matrix typically, and you try to find a solution, which means the eigenvector lying in the subspace B. So the classical approach for achieving this. So once you have the matrix B, what people do is Rayleigh-Ritz. So the idea is usually you orthonormalize the matrix. So you take the QR factorization, and then you look at the projected matrix, which is k by k, which is smaller. And then you can solve this eigenvalue problem from which you can extract the Ritz vectors or Ritz pair, approximate eigenvectors and eigenvalues. Once again, this costs you at least nk squared operations. Just the act of computing this matrix will cost you nk squared. The question, or our question, was, can we use sketching to speed up the process? And so you can't. So if you just look at this, it's not obvious how to use sketching to improve the speed. We basically rely on another classical result by Beresford-Poirot. He describes a nice way of looking at Rayleigh-Ritz in a different way. So you can understand Rayleigh-Ritz as saying you solve this least squares problem with respect to M, which is a square matrix, and then solve the eigenvalue problem with respect to M. And then that can be shown to be equivalent to Rayleigh-Ritz. But now, so once you look at this, it becomes quite obvious to how to try and sketch the problem. You would be just timesing a sketch matrix on the left. So imagine this is like 1,000,000 by 1,000. This becomes 2,000 by 1,000, something like that. So now we can consider solving this. And essentially, the algorithm is the same. You solve for M hat, and you solve the eigenvalue problem. And essentially, by the same argument, which I kind of didn't really talk about, sketching can only increase the residual by a factor 2-ish with high probability. So all is good, assuming you are able to get or extract good eigenpairs from M hat. And this is where things become a little bit complicated, or actually impossible, because Rayleigh-Ritz is something that everybody uses, but it's known to have pathological examples where it basically fails miserably. Even if the subspace has an exact eigenpair, you might end up with a Rebus eigenpair. And so obviously by sketching, we're not going to be overcoming that issue, but at least in terms of the possibility of getting a small residual, sketching is not going to harm. And then we indeed don't really see much loss of accuracy in our experiments, where we're solving a generalized eigenvalue. I'm sorry, a non-symmetric eigenvalue problem arising in optimization here. So here, speed up is more like 10 or 20, but it's a reasonable speed up that we can get. Once again, because we're not orthonormalizing a matrix, and we're avoiding essentially nk squared operations. Right. So 2 more topics. So Tikhonov regularization. So this is joint work with Mikey, who's there. so she can talk about this, but I will because I'm standing. I think most of you have seen this problem. So you're either solving a least squares problem, or it could be underdetermined actually. So A can be either very tall, skinny, or very fat. I mean, it could be square, but then there's much less opportunity to sketch, I suppose. So what we do is essentially sketch the precondition. So if you know blend and pick, essentially it's the same idea. But we take advantage of the fact that we usually need to solve for different lambda i's. So lambda I is like the regularization parameter. You don't really know in advance what value is going to be best. So you might be solving for like 10 different values or 100 different values. And we wanted to essentially reuse the same sketch to solve. So what we say is we can essentially take the sketch size to be at most as large as the smaller dimension of A. Sometimes even smaller if A has like a low statistical dimension, essentially like A has a low rank structure. And in light of my presentation today, I wanted to highlight that many previous papers work with a normal equation. So they start with essentially the normal equation for which is equivalent to that problem. But then once they do that, we all know that it's unstable. So if the matrix A is ill conditioned and lambda is not small, is rather small, then this can really hurt your accuracy. So we don't do that. We work directly with this linear system or least squares problem, and we precondition that using a sketch only of A, and then you can reuse the same a preconditioner for solving all the least squares problem efficiently, and then we do so in a stable way. So please go to Mike's poster. She's been talking to many already, but I'm sure she'll be happy to tell you more. Anyway, okay, so final topic is a null space. So this is a paper with my other student, Taejan Park. So here the assumption is we're interested in a null space of a very tall skinny matrix. So if you want null space or the smallest singular subspace, basically. So you're given a tall skinny matrix, you're looking for the singular vectors corresponding to the smallest singular values. So a naive idea, so this is like a very ripe for sketching. It's almost trivial how to sketch. So you times from the left a sketching matrix. So once again, imagine this was 1,000,000 by 1,000. We reduce it to 2,000 by 1,000 and solve the SPD problem for this. So this is basically just computing the smallest singular. So once you have the SPD of that SA matrix, you're done. The crucial question really is to argue how close your computed or sketched solution is to the desired solution. And for this, we're going to use a classical perturbation theory. We tried to use Davis-Kahan and basically like results by Stewart and Son. They weren't as accurate or reflective of the reality as we would have liked. And then we realized there's a very nice paper by Rankin Lee who talks about relative or multiplicative perturbation theory, and that really changed the sharpness of our results. So the preprint is on arXiv, so please take a look if you're interested. Right. So I'm sorry I went really fast, but I hope at least I kept with the time. So I wanted to highlight how exciting randomized linear algebra has been, and I think it will continue to be in the years to come. I really think the importance of classical stability theory will continue to or become more important in the process of developing them further. I think that I would like to highlight one of the key aspects of the work that I presented today is the notion of non-orthogonal linear algebra. So classical linear algebra has hinged very much on working with an orthogonal matrix like QR, algorithm, so on, for very good reasons, of course, and that automatically implies backward stability. But if you use stability results carefully, then sometimes you can work with a non-orthogonal basis, and that can sometimes really speed up the computation. Right, so thank you very much for your attention. I'll stop here.